So this is a lecture on Euler's equations. Given an equation in the following form, t squared y double prime plus alpha t y prime plus beta y equals 0. For t is positive, alpha and beta are all constants, and this is an equation, second order differential equations in terms of y and t. So far, we only learned how to solve a second order with constant coefficients. Notice that this coefficients here with coefficient of y double prime and coefficient of y prime are not constant, so we cannot use the method that we have already learned. How can we solve these equations? So how to solve these equations? First, we want to introduce x, a new variable x equals natural log of t. As I say, you're changing the independent variables from t to x. And once you have x, introduce x equals natural log of t, then you can find the relation between derivative of y and t to the relation of y and x, which is the following. So the first derivative, dy dt, should be equals dy dx times 1 over t. And the second derivative, dy squared dt, squared equals 1 over t squared of the second derivative of y in terms of x minus the first derivative of y in terms of x. We have derived these two equations in class. So then now we can actually transform the original equations in terms of y and t into a different equations in terms of y and x in this form. So you can see that now we have a second order differential equations in terms of y and x, where x is the independent variable, y is a dependent variable, and all the coefficients of y prime and y double prime are all constants. Now we have a second order differential equation with constant coefficients. We know how to solve this equation. We can solve for y in terms of x, and then we replace x by ln t, natural log of t, to solve for y in terms of t. And then we solve these equations. Let's do an examples here. The first example, if you want to solve for these equations, t squared y double prime minus 4ty prime minus 6y equals 0, notice that this is an Euler equation, is in this form. T squared is a coefficient of y double prime, and alpha here is negative 4, and then beta here is negative 6. Okay. Remember, in that form, t squared y double prime plus alpha t y prime plus beta t equals 0. Now we let x equals ln t to get a new differential equation in terms of y and x. So then the equation is in the form of y double prime plus alpha minus 1 y prime plus beta y equals 0. So it is actually in this form. And you can see that alpha here is negative 4 minus 1, and beta here is actually negative 6. Once you have, then you can find, sorry, I overwrite it here, but you can see that once you have this second order differential equations, then you can find the characteristic equations for this equations, because this it has constant coefficient, and the characteristic equation should be here's the characteristic equations is r squared minus 5r minus 6 equals 0, and then you can solve for r, which is r equals 6 and r equals negative 1. Okay. Now we can get a solution y in terms of x, which is c1 e to the 6x plus c2 e to the negative x. And then we can replace x by ln t to get y of t, which equals c1 t to the 6 plus c2 t to the negative 1. You see that you can cancel this term, cancel e and ln t. And here this is the final solutions, the general solution for that Euler's equation. So you can, at first you don't have to solve, but once you introduce a new variable x in terms of L and t, then you can solve for y of x, and then you can solve for y of t. Now let's look at the second examples here. You have a differential equation second order in this form, and you notice that this is an Euler equations because t squared is a coefficient of y double prime, alpha t is a coefficient of y primes, and then beta y. Again, the process is let x equals natural log of t, and then you get a new differential equations with constant coefficients in terms of x and y. Then you can solve for these equations by first finding the characteristic equations, which is r squared plus 6r plus 10, and then you get a complex roots, -3 plus minus y. Once you have a complex root, you can find the solutions y in terms of x, which is c1 e to the -3x cosine of x plus c2 e to the -3x sine of x, and then you just plug L and t into x to get solution y in terms of t. Cancel, simplify your functions to get the final solution to be c1 t to the -3 cosine of L and t plus c2 t to the -3 sine of L and t.